So welcome to the last session of this symposium, which is dedicated to the development of clinical diagnostic tools. So we will have 3 presentations by ESR 8, 9, and 10. And we will first start with the presentation of Murat Akkurt, who is working at the Vision Institute in Paris under the supervision of Françoise Baudouin. And I would like to mention that Murat started 1 year ago, and he joined the consortium of IT-DED in October 2020. So, Murat.
Hello everyone, good afternoon. I'm today really happy to be with you and to present my work that I did during last year. So my project is development of biomarkers for dry eye disease, and my presentation will be divided 2 parts. The first part I will mention my study with proteomic analysis of human tears that I use Schirmer strips and mass spectrometry technology. And in second part, I will give my preliminary results of with dry eye patients that we also conducted another proteomic study with these patients. So before start my work, I want to introduce briefly the dry eye disease. As you can see, it's a multifactorial disease, and many factors and conditions can start this self-stimulating vicious circle, like inflammation and neurosensory abnormalities are the main characteristic of the disease. Inflammation is the main mechanism of dry eye disease, and both innate and adaptive immune system involved in dry eye disease. So my first study is a proteomics analysis with human tears collected with Schirmer strips and analyzed with mass spectrometry. The aim of this study was to analyze human tears collected by Schirmer strips, and also analyzing proteome profile in 2 different parts of Schirmer strips. So as you can see, here this is a Schirmer strip. We consider the whole strip, and we also, after collection, we cut the strip into 2 parts. This part we name it bulb, and this is the rest. This part, as you can see, is the part in contact with conjunctiva to collect cells, and then the tear fluid with capillary forces move through the strip. And after this, we analyzed these strips using timsTOF Pro mass spectrometry. This is the methodology of my sample collection. In this study, we employed 2 healthy subjects, and we collected Schirmer strips over 2 days in 2 different time courses, in the morning and afternoon. And by grouping these strips, we try to prepare 2 homogeneous groups from each subject, each day and each time course. And in the first group, we consider the whole strips, and the one in the dashed lines, in this group, we divided strips to bulbs and rest. And then the protein solution were prepared. In the end, we had 3 different batches. After protein quantification and normalization to 500 nanogram, we processed these samples, initial to injection to nanoelute coupled to mass spectrometry, and with data obtained from mass spectrometry, we identified these proteins by using software called MaxQuant. Here is the first result, and in figure A we can see the number of identified proteins in the whole Schirmer strip. This one. So in the whole Schirmer strip, we identified 1,000 of proteins, but the same when we cut the Schirmer strips and we analyzed these 2 parts separately, we increased the number of identified proteins almost 50%. And in this part, we can see the comparison of these proteins in bulb and rest. You can see the half of these proteins were common, while other half either were specific to bulb or rest. And when we merge these 2 these 3 batches, we can see again the specific only to bulb and rest. And in total, we reach a number of more than 1,500 proteins identified in these 3 batches. So after identification, we were interested in the function of these proteins. Therefore, we did this analysis, and here you can see biological processes involved in TEER protein and molecular functions, and you can see cellular process and metabolic process were highly representative with more than 500 for cellular process, and binding catalytic activity were main subclasses of molecular functions represented with more than 300 proteins. In the second analysis, we analyzed protein classes of this protein, and you can see the most representative 5 classes. And as you can see, especially metabolite interconversion enzymes were more abundant in the bulb compared to whole strips or the rest of the strip. So among all the identified proteins in this classification, 41% of them corresponded to enzymes with a number of 480 in all 3 batches. And when we analyze the families of this enzyme, we can see hydrolyze is almost half of these enzymes, and the second major group is oxidoreductases, which are important in the homeostasis of tear film. And we were also interested in the major signaling pathways in homeostasis of tear film, and therefore we prepared this barcode figure. And here we can see apoptosis, complement, interferon signaling, lipid metabolism, cell junction. Here each bar represents 1 protein, and when we have this protein in all 3 batches, you can see like these are the common proteins, while other were common in 2, and like this and this were unique proteins to the batches. So by cutting the Schirmer strips, we can see that we could identify new molecular effectors involved in these major signaling pathways. And to give examples of this protein in proteasome, they were in apoptosis. We see that proteasome subunits were highly identified, and several complement factors in complement. Major histocompatibility complex class 1 in interferon signaling. We identified MMP9 and 7 in MMP signaling, and in cell junction some catenins and phospholipases. And again, here you can see we identified more protein in the rest of the strip that were involved in lipid metabolism. So to sum up, we could identify 50% more proteins by this methodology, cutting bulb and rest and analyzing them separately. We identified a huge amount of enzymes in TEER proteins, and it was a major enzyme classes. We also identified molecular effectors that involved in 6 important signaling pathways in ocular surface. This work is important because we show that this methodology using Schirmer strips and using this timsTOF ProMes spectrometry can be a suitable methodology for further candidate biomarker investigation involving in ocular surface diseases. And this study led to this paper, which are now under review, and we are looking for its acceptance. So now I will present the second part of my work, which involves in the proteomic analysis of dry eye patients. So again, here dry eye classification is basically aqueous deficiency and evaporative dry eyes. Here we employed Sjögren syndrome patients suffering Sjögren syndrome patients, which is a severe aqueous deficiency, and we know that also Sjögren is a kind of mixed of dry eye disease. Most of patients manifest a mixed form of dry eye disease of aqueous deficiency and evaporative dry eye. So briefly to describe, Sjogren's syndrome is a chronic progressive autoimmune system, and it mainly affects middle-aged women, and it characterized with lymphocytic infiltration of lacrimal gland and salivary gland, and as a result, no secretion of tear and salivary, and patient have oral and ocular dryness. And why we are interested in biomarker investigation in Sjogren patient, because the diagnosis still a challenge in Sjogren patient with current existed biomarker which are based on serum. The specificity and sensitivity is not as high as we expect, and to develop a better treatment options and more sensitive and specific diagnosis, we need more omics study. Here we can see demographic and clinical characteristic of Sjogren patients, and as you can see, there is a significant difference in signs and symptoms between Sjogren and healthy control. The samples were collected by Schirmer strips and analyzed with the same MS spectrometry. And the aim of this study was to investigate differentially modulated proteins in Sjogren patients versus control. The first result in this principal component analysis, you can see a significant proteome segregation between the Sjogren patient and healthy control. And in this volcano plot, we can see significantly modulated proteins. In total, they were 167. 58 of them were upregulated. These were the upregulated proteins, but majority were downregulated in Sjogren versus control. As you can see, some examples. When we analyzed protein classes of these significantly modulated proteins, in downregulated proteins, we see metabolite interconversion enzymes and cytoskeletal. Interestingly, they were major classes and different other classes. However, when we evaluated the upregulated proteins, we see the two major classes are both enzymes, and enzymes here in these upregulated proteins are responsible for 70% of these all proteins. And as a second classification, we analyzed the molecular function of this protein. We see a high number of modulated proteins in catalytic activity, and in binding activity, we see the majority of this protein were in downregulated part. And molecular function regulators such as protease inhibitors were also downregulated. So to sum up here, peptidase activity and nucleoacid binding proteins were upregulated, while proteins involved in oxidoreductase activity, protein binding, were downregulated in this group. So after having such a huge data in order to select the best targets of interest, we have to develop a strategy and criteria, and our strategy is based on the function of protein, their description in the literature, if we have already existed validation tools, and also the biological processes of these proteins are important because we are, for dry eye disease, we are interested in oxidative stress, programmed cell death, in this case cytoskeletal destabilization, because we find that many proteins were downregulated, and of course inflammation, neuroinflammation are important biological processes. And with the help of bioinformatic analysis, we can build a network and models, clusters, in order to decide for the best candidates for the validation. Here we can see 5 examples of these molecular effectors for further validation. We consider their protein classes, their function, and their in the literature if they are already described in some diseases to help us about their role. And today we have databases that can help us about the expression of these molecular effectors in the anterior segment of the eye. I take this information from a transcriptome database for healthy and diseased human eye tissue, and because I'm interested in these targets, their expression is important, and here I can see if their gene expression. So for example, here I can see that actinin 4 predominantly expressed in conjunctiva, and it can be a good molecule to have information about in conjunctival cells. And for nucleobinding too, I can see that it's highly expressed in lacrimal gland, so it can be a molecule for a lacrimal gland function. And these molecular effectors in our study, they were significantly downregulated, and you can see the mass spectral count of these proteins in healthy controls in green and in red in the Sjogren patient. So we can see either these proteins were even not identified in Sjogren patients, or they were really lowly identified compared to healthy. So for validation of these targets of interest, eventually we will work. I work with a human spaceman. I'm lucky here because I have access to human spacemen such as Schirmer strips, conjunctival imprints collected from dry eye patients, and at the same times I do in vitro model. So I work with human corneal epithelial cells with two model, pro-inflammatory and hyperosmolar stress model, and I also hope to be able to work in vivo model and having tissues of lacrimal functional unit, and eventually all these specimens will be analyzed with using different techniques for detection of proteins or gene expression or their localization and amount inside within the cell. Here I want to show you an example of my preliminary results. I mentioned actinin 4 in my among these 5 targets of interest, and we can see actinin 4 is a regulator of intercellular junction, and it also takes role in actin cytoskeleton cell motility, and we can see it's also translocate into nucleus, and here it interacts with different transcription factors, including NF-kappa B. So this is an important target for us for its involvement in these cellular processes. And first, I investigated is actinin 4. It can be detected in our samples, and we see that with samples collected by Schirmer strips, it can be detected because it's, as I shown before, it's expressed, gene expression already detected in conjunctiva, and it comes from conjunctival cells, we can say, but in the tear we couldn't detect it. And so in vitro dry eye model, I inducted my cells, human corneal epithelial cells, with interferon gamma in a dose-dependent manner during 24 hours. And I detected that actinin 4 is downregulated in a dose-dependent manner. And here you can see my experiments of immunocytochemistry. Again, after 24-hour induction with 10 nanogram of interferon gamma, I could observe that the filament of actinin 4 were disrupted, and the amount is also decreased. So to sum up, comprehensive proteomic investigation helped us to profile a proteome of both healthy and dry eye patients and make a comparison. And as in my first study, we could reveal molecular effectors involved in signaling pathways in healthy and homeostasis of ocular surface. And my preliminary analysis of Sjogren with Sjogren patient showed that we have a significant proteome segregation between healthy and dry eye patients. And we identified a high number of significantly modulated proteins. And when we analyzed the function of these proteins, we saw that the upregulated ones were more related apoptotic or catalytic activity, whereas downregulated were more related to cytoskeletal and actin binding proteins. And we also observed an alteration in the proteins of oxidoreductase and calcium binding proteins. And as the first part of my work, as I said, is under review, and I show already the preliminary result with actinin-4 that it's downregulated with interferon gamma. So we will choose more targets for validation and to see the effect of these models I mentioned before on these targets of interest. So I want to thank you, IT-DED Consortium, and Paz is not here, but also thank to Paz for her contribution to these events and during the projects for supporting us, and also to my group, Equipe here, Paris, and my supervisor, Françoise Boudois and Christophe Boudois, and also Kerima Kesal, whom I work closely with for their contribution to this also work. And thank you very much to all of you for your attention.
So thank you, Murat, for your very nice presentation. Do you have some questions in the audience? Yes.
Okay. Yeah, very nice work. That's a lot of in-depth stuff. A lot of this type of stuff has been done by Roger Byerman and Zolé in Singapore, and more recently, their collaboration with Hannu Satalo at Tampere in Finland. Their big finding was S100 proteins. Did you see that at all in your analysis?
You mean the results of this study?
Was that what they were doing? Yeah. So that was Marga's patients, right? Yeah. Yeah. But they did multi-toph mass spec as well in dry eye patients, and I was just wondering whether there was any overlap in the data.
Honestly, I didn't compare, no.
You did. Okay.
Okay.
Thank you.
I would like to ask about the quantitation aspect of your timsTOF Pro. I think that's a very nice instrument, extremely sensitive. So do you have an idea about which proteins are abundant and which one are lowly expressed?
Yes, we have different information regarding data obtained from mass spectrometry, such as intensity of these proteins or mass spectrum count. I also showed here I used mass spectrum count because it's easier to see. Like this one. Yeah, it's a semi-quantitative method, mass spectrometry, so we cannot say it's 100% certain, but it can give us an idea about their abundance.
Thank you for your nice presentation. I was wondering, maybe I did not follow completely. You said like 167, if I'm not wrong,
yes.
Proteins differ in your analysis, and then you showed 5 targets of interest.
Okay.
On what basis did you make that selection?
Yeah. Yes. Thank you for your question. Of course, yeah. When we have a huge number of proteins, we cannot validate all of them. So we first check their biological processes that they involve, and their function of these proteins, and if we have available validation tools, and based on this, we decide for like first selection. This was just an example, and then we continue with our in vitro studies and some spacemen from patients, and based on this data, if we have good results, we can go with further investigation. But if not, we then we select some other targets that are of interest due to their involvement in this biological process, such as inflammation, of oxidative stress, of programmed cell death, which is the case in dry eye disease. And yeah, basically due to their function and involvement in biological processes, we choose a selection, and if we have available validation tools.
Yeah, just out of personal interest, you showed that a lot of hydrolases were involved. Were among the hydrolases, did you have many proteases or?
Yes, I will say the majority of these hydrolases, when I investigated, they were proteases. That's true. majority is proteases, yes.
Yeah. And you didn't say anything about kinases, which you often find in a lot of these kind of studies where
kinases I grouped inside the transferases, so it's a subgroup of so I didn't want to show all sub-families of enzymes, so I prefer to show them in a 6 major family. So kinases also are there, but as a subgroup, they are in transferases. And transferases was the 3rd largest group in tier proteome.
Okay, thank you.
And after, okay, this one and after.
Murat, that was a very lovely presentation and a very ambitious study, if you don't mind me saying so. So many molecules, where do you start? But taking the actinin 4 as an example, when you showed us the data, can you go back to it? You said that it wasn't present in the tiers.
Yes, okay. Oh, sorry,
Maybe
this is not my presentation.
Maybe we've lost the present. Not to worry. But in that graph that you showed, there was no beta actin either.
Yes, because in tier we don't have cells, and beta actin is a housekeeping protein which is used basically for the detection of cells. And we discussed this also. For tier, we don't have a housekeeping protein. We cannot see beta-actin either, and normally beta-actin is used as a reference, and even I couldn't use beta-actin as a reference. And it was a question for me, because when you work with tier, then what's the reference protein?
Okay, so you could use maybe albumin?
Yes, albumin, or we can add some external protein.
Spike, you could do that too, but you're going to have a standard in there.
But since I particularly work with Schirmer strip, this is not a limitation for me at the moment, because I basically have a spaceman, as a human spaceman, I use Schirmer strips at the moment, and here, because I have conjunctival cells, sure. I have beta-actin and actinin 4 as well.
But your long-term intention is to work with the Schirmer strips?
Yes.
Yeah.
Because in Schirmer strips, I have a wider spectrum of proteins compared to capillary. It also includes tier and more than tier as additive cells also.
Sure. Okay, thank you.
Thank you.
Murat, a question. You showed in a table some clinical values comparing healthy controls with Sjögren's. If I'm not mistaken, the Schirmer test of 8 millimeters for a Sjögren, that is very unusual. I mean,
unusual, you will say?
I don't think I have a single Sjögren patient with that high values of Schirmer. So how?
I think it's really heterogeneous, and there is like when we even check each protein identified in each subject. It even varies, but I would say it's still low, but
no,
it's not as low.
My question is that when you try to publish it, you might be questioned if a clinician reviews the paper that this is. I mean, you have to have a lower Schirmer's in order to diagnose Schirmer test. That's very unusual, and you may be criticized. So you will have to explain that these patients were very well diagnosed with a biopsy and all that, because this is very, very interesting.
Okay, thank you for.
I understand why you did it. I mean, if you take Schirmer's from real Sjögren's, you will have 0, 1, 2, and you couldn't do much with.
I understand, but I thought also it can depend in which stage of the disease they are.
It is kind of mandatory to have a low Schirmer to diagnose, to rule out Sjögren as a cause of. You have to have dry eye and dry mouth, and then dry eye meaning lower Sjögren, and then you will go ahead with the analysis and the biopsies and all that.
But they had autoantibodies in their serum as well, so when they were diagnosed.
Yep.
So it's for us.
I'm just saying that you may be criticized, because the real protocol says that you have to have a positive biopsy, labial biopsy.
Okay.
With a certain criteria.
Okay, thank you.
Okay, the last question.
Yeah, we have a question from Philip Steven.
Okay.
So, how do you explain the increase of proteins after separating Schirmer strips into section A and B? I understood that they derive from the same batches as the non-cut strips.
Okay, so my theory is that by separating the Schirmer strip and eluting them separately, first we decrease the complexity of the sample. As you know, there are some major tier films like lysozyme, lactoferrin, which compose like 80-90% of the total protein amount. So when you divide it, you reduce the complexity, and it became a bit easier for the less represented molecules. And second, like for lipid-related proteins, we identified more in REST. I think such techniques also help you to identify the proteins related to lipid, because when you insert Schirmer strip, you first collect all the basal tier, which includes both lacrimal gland secretion, mucins, and also outer phase oil. But once this taken, absorbed, then you have only reflex tier, which is only aqueous phase, not lipid. So I think the lipid first absorbed, and the followed aqueous secretion move these lipids to the rest of strip. And in this case, you find the lipid-related proteins more in the rest part of the strip, and of course we decrease the complexity of the samples by this method.
We have to close the discussion after this very nice presentation. Thank you, Murat.
Thank you very much, all of you.